It's my honor to give a presentation within this group. And also today, my topic is about antiperovskites. Hybrid highlight lead perovskite has drawn a great attention recently because of its superior optoelectronic properties and the facile and low-cost preparation method. It has been reported yet the power conversion efficiency of hybrid highlight lead perovskite-based solar cell is over 25%, which is overpassed the traditional commercialized solar cells like silicon, cadmium telluride. But however, their biggest challenge for their maximum hybrid highlight lead perovskite-based solar cell is its toxicity and their instabilities. So to overcome their toxicity of lead, we direct substitution method and their cation mutation and lowering the structure dimension has been proposed as method. Beyond lead-free perovskite, highlight double perovskite, and the low-dimensional perovskite, antiperovskite is another choice to overcome the toxicity of lead. Antiperovskite can be obtained via ion tape inversion in their perovskite structures, and also which means the cation becomes anion, and the anion becomes the cation. And for this kind of antiperovskite, it maintains the perovskite structure and also show unconventional and intriguing properties, which triggers the investigation, such as luminescence and the superconductivities. In contrast to the intensive study of highlight perovskite and the double perovskite as photovoltaic materials, the investigation for antiperovskite as photovoltaics draw less attentions, but nevertheless, there's already some studies about the antiperovskite, about the hybrid antiperovskite, and also the inorganic antiperovskite compared to the flat band dispersions for hybrid antiperovskite. All inorganic antiperovskite shows much more improved band dispersion and also has a high optical absorptions for which are desirable for the photovoltaic applications. In our recent work, we find an overlooked linear relationship between tolerance factor and the various physical constants, which can be useful for designing antiperovskite nitride-based alloys. And we notice that this is the only one inorganic double antiperovskite has been experimentally synthesized and also investigated as superfast ion conductors for solid sodium-ion batteries. But for other pinicogen-based double antiperovskite, their optoelectronic applications hasn't been explored. As shown by the single antiperovskite, we can see for double antiperovskite, they may have a great attention as photovoltaics. So, inspired by this work, here we design a quaternary antiperovskite nitride. Since the antiperovskite can be transformed to quaternary antiperovskite by splitting the anion oxide atoms at A side or B side. So we obtained 48 compounds based on these compositions. Then we first focus on their phase stabilities of these 48 compounds. For A-side unordered compound, the type A configuration is the most favorable, which are the cubo of which the cubo octahedra are alternating along one directions, showing a layered structures. But for the B-side ordered quaternary antiperovskite, the favorable configuration is type F, which the octahedra are alternating along 3 directions. After identifying the favorable configurations, we go to the crystallographic stabilities. Since antiperovskite still maintain the structures of perovskite, so for double antiperovskite, they should satisfy the crystallographic requirement of the crystallographic stability. So the good Schmidt tolerance factor and also the octahedral factor, which leads to the discovery of 34 quaternary antiperovskite with their perovskite structures. This is a geometry constraint. For this 34 quaternary antiperovskite, we evaluate their thermodynamic stabilities by using the database from materials project, and also the calculated total energies of the target compound. We found that 18 A-side ordered compound and 3 B-side ordered compound showing their thermodynamic stabilities. Here, we set the criterion for energy above Hall at 25 MeV per atoms by considering the entropy, by considering the possibility of the entropy stabilization of metastable compounds. We further evaluate the dynamic stabilities for these 21 thermodynamically stable compounds, and we identify 7 compounds are both thermodynamically stable and dynamically stable. For ideal cubic perovskite and highlighted double perovskite, distorted variants are normal and they can be more stable than their cubic prototype. So here we will consider the structural distortions for this quaternary antiperovskite. But however, since the phonon spectrum calculation is very time consuming, so we will not consider the structure distortions for each compound, but we will first look at their electronic structures. If the compound have suitable band gap and very large band dispersions, we will study, but they are thermodynamic stable and dynamically unstable. We will look for the structural distortions for them. So we first made a benchmark for the experimental reported compound. Our calculated compound is 1.3, which are in agreement with the experimental measured optical band gap for magnesium nitride antimony, nitrogen antimony. And we use these parameters for 21 compounds to obtain their band gaps and also electronic structures. We found that both for A-side ordered and B-side ordered quaternary antiperovskite, they show a decreased band gap, and the band gap at the combination of the element at AA apostrophe and BB apostrophe become heavier, and also the X-side element become heavier. And also the band gap can vary from 0.6 to 2.6 eV. Such a band gap opportunity is a result of the composition flexibility. So based on the thermodynamic below criterions, thermodynamic stable, suitable direct band gaps, within the range of 1.0 to 1.8 and a good band dispersion around the band edge. We identify 6 A-side ordered compounds and 1 B-side ordered compounds. For this compound marked by green, which are both thermodynamic stable and dynamic stable. So we continue to introducing the structure distortion for other 6 compounds. Since group theory has been successfully employed in the study of oxide, perovskite oxide and perovskite halides. So here we also use the same method to study the relationship between the parent, the cubic tapes and also the distorted ones. We identify that for the A-side ordered compound, also for this 5 compounds, PMC21 is the ground state structures, and for the B-side ordered compounds, this is the ground state structures. Both for these compounds, they are dynamical, they are thermodynamical stable and also dynamical stable. After identifying the ground state structures of these compounds, we start the material screening process with respect to the target photovoltaic properties, like the small effective mass and the binding energies of exciton should be less than 100 eV, which would be facilitated to the separation of hole and electrons. And also the dipole allowed optical transition is very important for the photovoltaic materials. Based on these criterions, we identify 5 promising compounds. They also show high optical absorptions and their theoretical maximum conversion efficiency are even larger than, are comparable or even larger than maximum lead iodides. And it has been reported that for the representative highlight perovskite, cesium, silver, bismuth, bromide, and cesium, silver, indium chloride, they show 0D characters of electronic transport, since there was nearly no overlapping between the silver and the bismuth indium states, as can be observed from the p-dose. But for our promising compounds, quaternary antiperovskite, we can see all constituents, all components contribute to the valence band, which leads to a very strong hybridization in all 3 directions. And the conduction band minimum is dominant by the cation. So even though the A-side and B-side quaternary antiperovskite shows alternating cube-octahedral or octahedral in 3D dimensional, actually they can show efficient carrier transport in their 3D structures, which are quite different from the highlighted double perovskite. Since it has been in previous work suggested that large dielectric consistence has been contributed to the long Kerr lifetime and the long diffusion length in maximum lead iodides. And as our calculate the statistic dielectric consistence of these 5 promising compounds are even larger than the than highlight double perovskite and the highlight perovskite. So it suggested that the stronger in these promising compounds, there may be a very stronger dielectric screening, which can reduce the Kerr scattering and also trapping by their impurities or traps. And also it has been reported that the mixed ionic covalent band is very useful for the high performance of lead perovskite. So here we find that we predict the compound also show the same behavior, and also the A site elements plays a neglected role in this compound. Previous work are focused on the problem to overcome the difficulty, to overcome the toxicity of the lead. Here, this work, we wanted to stress the instabilities of the lead-based perovskite. We investigate the effect of atmospheres on degradation mechanism of the representative hybrid lead-based solar cells. They show different behaviors on the vacuums and also under one atmospheres of nitrogen. So we stressed that one atmosphere of nitrogen should be used for future preparation of hybrid perovskites. In this presentation, we first show a linear relationship between tolerance effect and various physical quantities of antiperovskite nitride, which may be helpful or useful to design antiperovskite nitride-based alloys. And also, while ionic tape inversion and anion ordering, we design a series of quaternary antiperovskites. They show good phase stability against decomposition and wide range tunable band gaps. And we identify 5 new stable optimal compounds as observers in single junction solar cells. Also, we introduce our work about how to avoid the instabilities of the lead perovskite solar cells. Thank you for my co-authors, and so thank you for your attention. That's all.